Yes, guys, back to the question. So we say that the probability of getting a first digit, which is a 5. What we'd have to do, we'd have to look at the table and determine how many cars do we have with the first digit being 5. Can anybody give us the answer to that? Looking on the table, looking on the table.
1, sir.
Remember, the top row records, all of those are first digits now. So the record of first digit being 1 would be this. And remember that the frequency tells you how many times this first digit 1 occurs. The first digit being 2, the frequency tells you how many times the first digit 2 occurs, and so on. So I'm asking you now, how would you be able to use this table to determine the probability that the first digit would be a 5? As well as, after we have finished that one, we'll look at the probability of the first digit being higher than 6 or more. Now, how many first digits have these students recorded in total? What's the number of first digits these students recorded in total?
9.
No, it wouldn't be 9. You have 9 different first digits, but it's not 9 digits you record in total. How many first digits are 1?
38.
38. So we have 38 first digits that are 1. How many first digits are 2?
27.
Right. How many first digits are 5?
22.
All right. So what's the total number of first digits that were recorded? How many first digits? Say that again, Miss.
So I was asking to repeat the question.
So I was asking, how many first digits are there in the entire survey?
So 38.
How much?
38.
Anybody hear what Miss Brown just said? Can somebody tell us what Miss Brown said? How did you arrive at your number, Miss Brown? If you go back to when we were doing statistics, guys.
The first, is it 200? Is that 200? 200?
In your calculation, you got 200?
So I got 180.
All right. So what you do to get the 180? Mr. Adams, that you did to get your 200?
I added all the frequency
I
numbers.
added all of them. Yes.
All right, so yes, so you should add all the frequencies. But the only discrepancy is that Ms. Brown getting a different value from you. So could you guys check it and make sure that it is correct, whichever one of you? Can I get more than one person? Adding up all the numbers in the frequency.
I just checked over, sir. It's 200.
It's 200. Mr. Adams got 200 as well. Anybody else can confirm that we have 200 when we add all the frequencies?
Yes, sir. I got 200 as well.
All right. So now if we are trying to find the probability of the first digit being a 5, how would we calculate that? So the probability of the first digit being a 5 is equal to what? What over
22.
what?
22 over 200.
22 over 200. Can we simplify that into a much simpler fraction? What this would work out to be? This would work out to be what? Can we cancel out 22 over 100, guys? What can go into 22 and 200? 2 into 22 will give you what?
11, sir.
And 2 into 200 gives you what?
100. But sir, question, how did you guys get the 22? I'm lost there. Don't miss up here.
If we are calculating the frequency of getting a first digit of a 5, we need to know
Oh,
the first digit is a 5.
okay, okay.
And
So you
so
use that 22 in the frequency?
yeah, because the frequency tell you how many 5 you have.
Okay, sir.
So that's how we get the 22 over 200. And so that would be the probability of getting a 5. Now the other part of the question, so that would satisfy part A. Part B now, asking what is the probability that the digit is 6 or higher? Can somebody calculate that and tell me?
Sir, would it be 64 over 200? 64 over 200, it is.
All right, so remember it asks you 6 or higher. So what we would do now is to look at how many frequency for 6, how many frequency for 7, how many frequency for 8, what's the frequency for 9. You add up all of those, you'll get 64. All right, so that will give you the probability 64 or higher. All right, sorry, 6 or higher, not 64. So the probability is actually 64 over 200, and that in terms of decimal work out to 0.32. Is that clear, guys?
Yes, sir.
Okay, good. All right, moving along. Now, in probability, we have what we call mutually exclusive events. Now, we say that two events are mutually exclusive if they cannot occur together. If two events cannot occur together, they are said to be mutually exclusive events. Can somebody think of two events that cannot occur together? Can you get in rolling one die? Can you get a 3 and a 4 at the same time? If you roll a dice, students, or what we call a dice, can a 4 and a 3 occurs in one roll?
No, sir.
No. No, so it means that that would be what we call a mutually exclusive event. You cannot have both of them happening at the same time. You either get one or the other, right? Now, when we are calculating the probability for mutually exclusive events, we say that we either have the probability of one or the other. So in the case where we talk about event A and event B, we can either have the probability of A or the probability of B, and from a set notation that can be represented by the probability of A union B. All right, now before we look at the Venn diagram relating to that, what you have to know is that for mutually exclusive events, when you're finding the probability of mutually exclusive event, you would have to add the two probabilities. So if you have the probability of A occurring, either A or B can occur, then to get the total probability of the two events, you have to add probability A with probability B. All right, so that's how we treat mutually exclusive events. Now, this is how the Venn diagram of a mutually exclusive event would look. And as you know, if you recall what kind of diagram is this, there's no overlapping of the two circles. And so what happening in A does not have anything with what's happening in B. And so this is a disjointed set. So you can't have A and B happening at the same time. They have to be at separate times. So this is how we represent it on a Venn diagram. All right, now this is an example of a mutually exclusive event. So a die with faces numbered 1 to 6 is rolled once. What is the probability of obtaining either a 3 or a 4 in a single roll? So we know that we can't get the probability of 3 and 4 at the same time. We can either get the probability of a 3 or a 4. So when they ask what's the probability of a 3 or, and the key word there is or, so that tells you that the event is mutually exclusive. So the probability of 3 or 4, then you would have to find the probability of getting a 3, which is 1 out of 6. Then you find the probability of getting a 4, which is 1 out of 6 as well, because you only have 1 3 on the dice, as we would say, and we have 1 4 on the dice. So there's only one possible 3 you can get out of the 6 faces of dice of the die, and one possible 4 out of the 6 faces on the dice. So the probability of getting a 3 or a 4 is simply the probability of the 3 plus the probability of the 4. So you would add both probability, which is 1 over 6 plus 1 over 6. And if you add 1 over 6 plus 1 over 6, you get what? 2 over 6. And then now when you cancel that down, 2 into 2 goes 1 time, and 2 into 6 goes 2 times. Sorry. 2 into 6 goes 3 times. Then the probability would become 1 over 3. All right, guys? Any question about this? So when we're looking at mutually exclusive event, you have to look for the keyword or. So the probability of one or the other, where both of them cannot happen at the same time. All right, so we call them mutually exclusive events. All right, now in general, a general formula for exclusive event. So if we want to find the probability of E1 or E2 or E3 or E4 up to a number of E's, let's call it up to En, all we would do is to add the probability of E1 plus E2 plus E3 plus E4 all the way up to En. So that's a general, what we call the addition law of probability. So addition law of probability applies to mutually exclusive events. All right, guys? Now, here they said, determine the probability of drawing an ace or a jack or a king of spade. The probability of drawing an ace, a jack, or a king of spade. All right, so how we work this out? Now we know the probability of drawing an ace. We have 4 aces in the card pack and we have a total of 52 cards. So you calculate the probability of getting an ace, which is 4 over 52, which is also 1 over 13. The probability of getting a jack, you have 4 jacks in the card pack, 4 over 52, same as 1 over 13. Now the probability of getting a king of spade. Now how many king of spade do you have in the pack? You only have 1 king of spade in the pack, so you'd have 1 over 52. So if we are to find the probability of drawing a jack, an ace or a jack or a king of spade, then pretty much what we're going to do is to add the probability. So probability of ace, and remember we say that once you have the R between them, probability of ace or a jack or a king of spade mean that you're going to add the probability of each of them together. So you add all the probabilities. And if you add it based on the fractional representation here, all of them are over 52. So 4 plus 4 would be 8 plus 1, which give you really 9 over 52. And 9 over 52, if you convert that into decimal, dividing the numerator by the denominator, you simply will get just 0.17. All right, guys? So that is what, this is how we calculate mutually exclusive events. All right, so moving on. So we are now looking at what we call non-mutually exclusive events. So if mutually exclusive events mean that they cannot if mutually exclusive event means that you can have the two probability in a single event, then non-mutually exclusive event. So they said that if it is possible for two events to occur at the same time, then the two events are non-mutually exclusive. Now, so in terms of getting probably a king of spade, right? So you can get either a king, or you can get a spade, or you can get a king of spade. That means the two of them can happen at the same time. So it's a non-mutually exclusive event. And from a Venn diagram point of view, you would have an overlapping here, because you can have either the probability of A or the probability of B or the probability of A and B in the middle. So that situation is what we refer to as non-mutually exclusive events. Now, when we are calculating the probability of non-mutually exclusive events, we can have the probability of one or the other or both. So this is what makes this one different from the mutually exclusive events. In a non-mutually exclusive event, you will have both, right? In a mutually exclusive event, you won't have both. So once I ask what's the probability of A or B or both, and if A and B can occur at the same time, in the case of a king of spade, a king can happen and a spade can happen at the same time in one draw, then we know that we are dealing with a non-mutually exclusive event. Now, how we calculate the probability of non-mutually exclusive events kind of follows a similar pattern to when we are doing Venn diagrams for two sets. Now, when we are dealing with Venn diagrams for two sets, we would generally find what we would say the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. Now, for probability, we are doing similar thing. So we're saying we are finding the probability of A plus the probability of B minus the probability of A times B. So remember now, this is not an intersection thing that we're really looking at here. We're just multiplying the product of the two probabilities and subtract it from the sum of the two probabilities. All right, let's just see if we can look at an example relating to that. So this is the Venn diagram here. And let us see what this example is saying. So in this example, if E1 is the event of drawing a jack and E2 is the event of drawing a diamond from a pack of 52 playing cards, find the probability of drawing a jack or a diamond or a jack of diamonds. So in other words, they are saying find the probability of jack or a diamond or the probability of both jack and diamond. All right. So what we say that we would do, we would add the probability of a jack plus the probability of a diamond. And because jack of diamond is non-mutually exclusive, we're going to find the product of the probability of a jack and diamond and then subtract it from the sum. All right, so if we look closely here now, the probability for a jack, how many jacks we have in the card pack? We have 4 jacks in the card pack, so total cards is 52, so we have 4 out of 52 for the probability of a jack. Now the probability of a diamond, now we have 13 diamonds in the card pack, so we have 13 over 52. Now the probability of getting both at the same time, we would have to multiply the probability of jack times the probability of diamond. Now, what we do then, we add these first two here. We multiply these two. So when we add the 4 the numerator as 4 plus 13, we get 7 over 52. Now, when you multiply 4 over 52 times 13 over 52, so that would work down. If we cancel it down, somebody can probably quickly work with their calculator. So we would have 4 over 52 times 13 over 52 all right. Now, you can see if you can cancel down anything here. Can we cancel anything?
Yes, sir. 4 into 52.
All right, so 4 into 4 goes 1. 4 into 52 goes 13. And 13 cancel with 13. So what we have left is 1 over 52. Do I see that? So now we would have what? 17 over 52 subtract 1 over 52. So 17 over 52 minus 1 over 52. 1 from 17 give you what? 16 over 52. Can we simplify that? 16 over 52.
Yes, sir. Divide by 4.
16 goes
4 times
4, and 4 into 52 go
13.
13. Right. So that would simplify it into 4 over 13. And if you give it as decimal, you divide the numerator by the denominator, which is 4 divided by 13, you will get 0.308 in terms of decimal. Is that clear, guys? Any question? All right, so let me clear what we have here. Everybody's good with this one, guys? Raise your hand.
Sir?
All right, Mr. Adams?
Yeah, that's him. Not 100% clear, but I'm sure after going through this video over again, I'll get some clarity.
All right. Okay, so all you need to focus on, Mr. Adams, is whether or not the probability that you're dealing with is a non-mutually exclusive event. And in order to determine whether or not you have a non-mutually exclusive event, you will see that the two events, Jack and Diamond, they can occur separately or they can occur together in one single draw, right? Because you have Jack of Diamonds. So you can get either Jack or Diamond or a Jack of Diamond. So in terms of Jack, we have 4 chances of getting Jack out of the 52 cards. In terms of Diamond, we have 13 chances of getting that. Now the Jack of Diamond is that in order to find this one, because this is a non-mutually exclusive event, because you're getting both of them at the same time. So we have to multiply those two probabilities, which is the same probability that we have for Jack and Diamond that we are multiplying. So we're multiplying the 4 over 52 times the 13 over 52. All right, so we're going to add the first section. So we add them both. Then we subtract the product of the two of them. So we add the two probability, then subtract the product of the two probability. All right, Mr. Adams. So that's pretty much the procedure. Follow?
Yes, sir.
And from there, you just simplify them down into the various fraction by doing some arithmetic manipulation. All right, so with that said, let us look at the next slide. So here now what we have what we call independent events. Now, so I want you to, when you go back through this video, make sure you know these events differently. We have mutually exclusive, we have non-mutually exclusive. Now we have independent. And after this independent, we're going to look at what we call dependent event. So what is an independent event? Now an event is an independent event is one which has no effect upon the subsequent event. Now, what do we mean by that? Whatever happened in the first event don't affect what happened in the second event. So in other words, if you have a bag with 10 marbles, 4 are blue and the remainder are red. So we have 4 blue marbles and 6 red marbles. Now, if we are going to draw a marble from the bag, what would be the probability of getting a blue marble? It would be 4 out of 10. Now, after that first event, if we are to draw another marble, what would be the probability of getting a red marble?
How many of the marbles are red? 6.
6 red
The
marbles.
others are red.
We have 4 blue and 6 red.
So the probability would be 6 out of 10.
Over 10, right. Now, suppose in the first event, we did take out that first marble and did not put it back. Would we get 6 out of 10?
No.
We would get 6 out of 9, right?
Yeah.
All right, so is where we put back the marble, it did not affect the probability of getting a red marble. Because we put back the marble, that means the total amount of marble that we have in the bag did not change, because after we draw, we put back. All right, so that is for the case of independent events. So once whatever was taken out of the bag or out of a sample is replaced, then the event is independent. So now with that said, if we take if we take out, if we do a draw and replace, then we have independent event. But if we do a draw and we don't replace, that means the next probability going that we're going to have will depend on the first probability, and so it becomes a dependent event. So that's the difference between an independent event and a dependent event. In the independent event, you do your first draw, you put it back. So the second draw that you're going to get will not be affected by the first draw. For the dependent event, if you do your first draw and don't put it back, then the event that follows will be affected by what happened before. And that's why we call that dependent event. All right, so if we are calculating the probability for independent events, well, notice now that in this case, when we have independent event and dependent event, it would be one draw followed by another draw or followed by another draw. So this is different in the sense that we are doing one event, then another event, then another event. So it's not like in the case where when we're looking at mutually exclusive, we are just looking at the possibility of doing one single event when we're doing mutually exclusive or non-mutually exclusive. But for independent event, you have one event followed by another event. All right, so in other words, if you have a coin, you would toss a coin one time, followed by the next tossing of another coin. And that would be an independent event, because what happened in the first toss of the coin does not affect what the probability going to be in the second toss. But in the case of a bag of marbles, and you pull out a marble for the first event, then you pull out a second marble for the next event, then what happened on the second event, the probability will be affected by what happened on the first event. All right, so in terms of the calculation of independent events, you simply just find the product of the two probability. So if you have an event A followed by another event B, and you're finding the probability of both events, you just find the product of the two events. So in this case, you're finding the probability of event A and the event B, event A and event B in two or more consecutive draws. Here we have a fair coin is tossed and then a card is drawn from a 52 deck of playing card. Now my question, would this be an independent event or a dependent event? Do we have an independent event or a dependent event, guys? Anybody? Will tossing a coin affect what we draw from a deck of cards?
No, sir.
No, so these two events don't have anything to do with each other. One won't affect the other. So if one won't affect the other, then the event will
Independent.
right. Now for independent events, we find the probability of one event and the probability of the other event, and then we multiply both probabilities to get the probability of the two events. So in this case, the probability of getting ahead is a half, probability of drawing an ace is 1/13. So the probability of an head and an ace would be a half times 1/13. And so you multiply the two probabilities. So your numerator is 1 times 1, you get 1, 2 times 13, you get 26. So you get 1/26. And if you divide 1 by 26 in decimal, you get 0.038. All right, guys. So that's an example of an independent event. Now, for independent events in general, if you have the probability A and B, and notice that for independent is generally and that you have, not or, right? So if you find the probability of A and B and C and D, what you do, you simply find each probability and multiply them together. That's when you're dealing with independent event and